that? Okay. Good morning. I'm Rich Vincent. Is this on? Yeah. Up. Okay. Hey, good morning. I'm Rich Vincent from Research Division at ARB. And we're here today for a seminar that marks the end of another successful grant project run by the Innovative Clean Air Technologies Grant Program. That's ICAT. ICAT co-funds the demonstrations of new technologies that have some promise for air pollution control in California. About 5 years ago, we had a very interesting application from Altex Technologies of Santa Clara for a new kind of low NOx burner. It got very good reviews, and the project was started off with high hopes, but because of some business problems, they weren't able to complete the project. They weren't able to do the demonstration phase. Subsequently, a couple of years ago, we got another application to complete the project. This was from St. Johnson Company of Berkeley, also known as Innovative Combustion Technologies. And the board agreed to take the residual funds from the incompleted first project and apply it to resuming the project and actually doing a demonstration of this new low NOx burner. And despite the passage of time, the technology still looked innovative, still looked very promising, and that has come to fruition with a successful project. We have with us today to deliver the seminar Mr. Dan L. Wiedemann, president of St. Johnson Company in Oakland. Mr. Wiedemann has been with St. Johnson since 1985, and before that he was with combustion engineer with Maxon Corporation. He holds a BS in electrical engineering from the University of Wisconsin. So, Mr. Wiedemann.
I think these are on. Thank you, Rich. I'd like to welcome you to this presentation this morning, the purpose of which was to field install and field prove laboratory technology that, as Richard already pointed out, had been proven several years ago by Altex Technologies. Rather than waiting till the end to give some credits, I thought I would acknowledge the efforts of the people that were involved in this project and kind of introduce you to these companies. Our company, St. Johnson Company from Oakland, has been doing business in California since 1903, originally as a fuel oil distributor, and then that led into the design and manufacturing of oil burners, and then into the 60s into gas burners, and so on and so on. So the company's been around for quite a while, involved in the combustion industry. Altex Technologies, who really are the holders of the technology, the IP for what the technology that was used in this particular project. There was some additional support from California Dairies, from their Tipton plant, and this was the host site for this field demonstration. And we certainly like to express our gratitude to them for putting up with us for the last year or so. And Molman Boiler Technologies out of Fresno, who was the installing contractor and also helped us straighten out a few little problems along the way. We also received a lot of help from Reliable Emissions Measurements out of Fresno, who has EPA compliant. They are actually a third-party source testing organization, and they graciously showed up on the job site numerous times with their EPA compliant equipment so that we could ensure ourselves that the numbers we were seeing were accurate. And of course, the California Air Resources Board with the matching grant funds, without which I'm sure this project probably would not have proceeded to the point where it is now, and as a result of this project, it certainly looks like we're going to be able to offer California industry some real advantages of single-digit NOx combustion equipment, but with some added advantages over and above what is currently available. We're no doubt all aware of the benefits of reducing NOx emissions, that being acid rain and smog and our health. But I think what we really want to look at is what are the costs involved in obtaining these benefits. A lot of these single-digit low NOx available today are operating at a very low efficiency. And we're going to go through all of these points in more detail later, but operating at a lower efficiency certainly has been one of the costs at achieving these benefits. A lot of these new systems are extremely expensive, not only up front, but the continuing operating costs are significantly higher than the standard combustion systems. More maintenance involved, and last but certainly not least, safety issues. In the past several years, there's been several incidents that we are aware of where people installing these new low NOx burner systems have run into some problems, and it has resulted in some property damage. To my knowledge, there hasn't been any personnel injuries or loss of life, fortunately. But we're going to want to take a look at all of these costs and see if we can't provide all of the benefits that the existing equipment is providing, but to lower these costs involved so that we can tip these scales back in favor of the benefits as opposed to over on the side of the cost. We'd like to look at some general categories of the types of ultra-low emission burner systems that are available today. Massive FGR burners. Well, what we mean by that, some of these systems, the massive FGR burners recirculate a very high percentage of the stack gas back through the combustion zone in an attempt to control NOx. Second major category that we're going to look at are matrix burners. And these are burners where the fuel and air is premixed at one point and fed through usually a long cylindrical porous matrix material. The next one we want to look at is post-combustion treatment, which does not involve burner design, but merely is taking care of or eliminating NOx that's already been created on the back end of a boiler system. Now we say proposed, and I would have to say that as a result of this project, and perhaps proposed is not the correct word, maybe we should say that this, rather than proposed, this is going to be technology that will be available, and in fact in certain sizes is available right now. And we like to think of this new technology as molecular modification during the combustion process in conjunction with staged combustion and the use of some moderate amounts of FGR. Now if we take a look at these general categories and just kind of briefly go over some of the features and what we think are some of the cons of these different massive SGR burners, and these are the ones, as I mentioned, that circulate a rather large percentage of the flue gas back through the flame. Some of them can recirculate as much as 40% of the total stack flow. Problem with this, very high electrical costs. You want to recirculate these large volumes of flue gas at fairly elevated temperatures. It's going to require some horsepower. And certainly we'd like to. And during this project, it became apparent to us that the horsepower requirement for recirculating flue gas on what we call the RX series is approximately half of what it is for these massive FGR burners. One other drawback of recirculating high amounts of FGR, the flame tends to become rather translucent when you're recirculating these products of combustion back through the flame. The translucency can create a couple of problems. One, it reduces your radiant heat transfer through the furnace into the boiler, and also it makes it a little bit more difficult to use standard equipment for detecting the flame, because the radiant energy, particularly the ultraviolet energy, is diminished considerably. Some of these systems that operate with large amounts of FGR will operate with staged combustion, and by that we mean you're burning a rich fuel-air mixture in one area and a lean fuel-air mixture in another area, which is fine. It's a good approach, but some of these systems that are trying to approach or have approached the single-digit NOx emissions levels have run into some problems, and we're going to get into that in a second. Other systems take a different approach, and rather than staging the combustion and operating very rich in some areas, very lean in other areas, they attempt to develop a near perfect mixing situation with the fuel in the air. And theory behind that is to avoid having any excess oxygen molecules exposed to the fuel. Combustion instability has been a problem with these systems, particularly on these staged combustion systems. When you're operating very close to the limits of flammability of the fuel, and then in addition you're adding FGR to slow down the combustion and lower the flame temperature, it's a very tricky concept, and things can go awry. And as a result, what these people have found is that it's been necessary to slow down what we term the modulating rate, which is the amount of time it takes to modulate the fuel input between the minimum and maximum values of the system. Problem with that is the load demands on boilers obviously are and in fact the San Joaquin Air Quality Management District last September, when they came out with their new regulations, specifically load following boilers for this very reason, because these particular systems cannot change firing rate fast enough without getting unstable and unsafe. And on these, what are now termed load following boilers, the emissions requirements have been relaxed somewhat. Okay, a brief look at some of the pros and drawbacks of these porous matrix burners. Now, as I mentioned, these types of systems pre-mix the fuel and air at one point, and then they feed it through this matrix material. There's several different types of materials. We say delicate and expensive because some of them are quite delicate. They're ceramic materials. They can break quite easily, and they're not cheap at all. The purpose of these matrix materials, there's little pores through them, and this fuel-air mixture is forced through these pores. The actual combustion takes place on the surface of this material. And we're going to go into some of the cons of doing that. Now, burning on the surface of this material does a pretty good job of extracting heat from the flame, which is one good technique of reducing NOx emissions. However, to achieve sub-9 NOx emissions, just burning on the surface of this material is not good enough. So these types of systems use a very high amount of excess air, which further reduces the flame temperature. And what's the drawback of all this? Well, here again, high electrical usage. You've got two problems here. If you're moving 65% more air than what's required for combustion, obviously your fan requirements are going to go up and the horsepower requirement is going to considerably. And also you have to force this fuel-air mixture through these little pores in this matrix material, so the pressure requirements and thusly the fan requirements are increased as well. We've run some tests on these types of systems, and in fact at the same plant for this project. And what we found was that the efficiency of these porous matrix systems that were in operation in this plant were running at 73%, as opposed to the 82% for the equipment that we put in this project. Well, that's a 12% additional fuel requirement that the customer has to purchase and burn for the same amount of output on the boiler. For this particular boiler that was involved in this project, which was 500 horsepower, and at this plant, which really operates 24/7 at an average of what we determined over the course of the last year to be about 60 to 65% of its maximum capacity, this difference in efficiency equates to more than $70,000 a year in fuel costs just for one boiler for this plant, and they've got 5 boilers. So a significant factor that we really want to address in this new technology. Also, because this matrix material has these small pores, they can easily become contaminated and plugged with any particulate matter that's in the combustion air. Might not sound like such a drawback, but if you talk to customers who have to change many filters on their combustion air fans every week, and if you don't do it, you're going to have a real big problem, but it is a maintenance problem. Also, the durability of this matrix material is somewhat questionable. And there are different types of materials. As I mentioned, there's some ceramic matrix materials. There's also some, I wouldn't say exotic, but stainless matrix materials that are available. But the lifespan of these things is limited with the combustion taking place right on the surface of this material. Now, if this material does fail, it can present a real large safety issue, mainly because, once again, you're mixing the fuel and air over here in one point, and you're actually combusting it at a different place. Now, in order for that system to work safely, the velocity of this fuel-air mixture that's being fed to the flame has to be higher than the rate of flame propagation coming back towards the mixing point. And what happens is, if this matrix material fails, the velocity of the fuel-air mixture going towards the flame front drops drastically, and the flame front comes back to the mixing point. So that's one of the safety issues that we wanted to address in this project. Also, these types of systems have a rather limited turn-down ratio, and turn-down being the ratio of the maximum input of the system to the minimum input of the system. Typically 3-to-1 is about out of one of these porous matrix systems. In the testing that we did on the system, we were able to get a 5.5-to-1 turn down, which was a little bit less than our goal, and we feel that there were some problems associated with this specific installation, which which kind of led to that. We were actually shooting for 6-to-1, and we believe that that can very easily be done with a few minor changes in that installation, or in future installations, I should say. Okay, we'll take a quick look at the post-combustion treatment. There's really two major categories here. The SCR, which maybe you've heard of, selective catalytic reduction, which uses a catalyst material and also the injection of a chemical, which creates chemical reactions to reduce the NOx. These things typically operate at relatively low temperatures, 5 to 850 degrees. They're very, very effective at removing NOx. 90+% removal. NCR systems, selective non-catalytic reaction. No catalyst, but still a chemical injection. These operate at much higher temperatures. They're not nearly as efficient at removing NOx. And I'd like to note that this 50% removal rate shown here is only if you can withstand a relatively high amount of what's called ammonia slip or chemical slip, and that would be the chemical that's being injected to reduce the NOx is not controlled properly or is not mixed properly with the effluent, and so you get what they call the slippage, and a certain percentage of this chemical then goes up the stack along with the flue gas. Now, some of these systems, if you need to limit your what they call ammonia slip to several parts per million, they may only be closer to 30% effective at NOx removal. Some of the chemicals that can be used, ammonia is the most common, sodium hydroxide or urea, or a couple of others that you can run into. Now, what we feel are some of the drawbacks here. There's the biggest one is the cost. Extremely expensive systems, very, very expensive. Not only for the equipment itself, but the constant operation and cost of the chemicals, et cetera. And particularly if there's a catalyst involved, which has a limited lifetime. Some of these things can also result in chemical waste streams, which need to be dealt with. Certainly would rather not have to deal with that if we can get away with it. Now, in order to control the exact amount of chemical that is injected into the flue gas, there's some rather elaborate sensors and control systems that are required to do this, and this is one of the reasons why the cost is extremely high on these systems. So, our goal in this project, we want to minimize these costs as much as we can and still maintain these benefits that we talked about a short time ago. We want to increase the efficiency. We want to lower the cost to the industry to make these benefits of low NOx a little bit more palatable to industry as far as the cost is concerned. We want to improve the reliability of the equipment, and that would relate back to catalytic beds that need to be replaced, matrix materials that may fail and need to be replaced. And, of course, the safety, which we touched on earlier with the unstable combustion conditions and also with this matrix failure. Now, on the efficiency side of things, what we found is that we could operate this new burner design optimally with 3% oxygen. We have actually operated at much less than that, down to 1.5% oxygen, but 3% is considered kind of optimal as far as industry is concerned, because you still have to deal with humidity changes, temperature changes, and whatnot, and operating down at 1.5 or 2% oxygen is cutting it a little too close. But at any rate, we kind of touched on this efficiency thing before and what it can mean to industry. And here again, under these conditions at this host site, more than $70,000 a year just in one boiler to put up with this this excess air that that is required on some of these matrix burners. Okay. One of our other goals in this project was not just to reduce NOx that we had already made, but we wanted to greatly reduce the production of it in the first place, rather than just trying to put a Band-Aid on the back end. So by producing less in the first place, it makes it a lot easier for us to get the final result down even lower at a lower cost. Now, we're going to be taking a look at just exactly what this looks like mechanically in a little bit more detail here, but it involves some multiple flame zones. And we are actually operating with 5 different flames in what we call 3 different combustion zones in the system, which we feel gives us a lot more stability and gives us this higher turn down ratio, and also eliminating this what we're going to get into in a little bit here is the formation rather than just dealing with thermal NOx, which most systems deal with. Okay, we felt we could lower the cost to industry on these systems by getting away from some of these exotic and very expensive materials, and of course the any chemicals that are required for post-combustion treatment. Also, the operating costs, we talked about the stack losses. This would relate back to the amount of excess air and the O2 levels in the stack, 9% as opposed to 3%, which is considerably more expensive to operate with all this excess air. And also the electrical costs to operate with these with very high FGR rates on these massive FGR burners. Now we're going to take a look at some numbers here. These were numbers that were put together by Altex Technologies several years ago, which represent the cost to remove 1 ton of NOx. And this is for initial equipment cost and operating costs over a 10-year period. And as you can see, way up on top, post-combustion treatment is just extremely expensive, almost 10 times as much as what we feel we're going to be able to do this at. Now, I want to point out this is for new boiler systems. The costs do change a little bit on retrofits. Doesn't change for the post-combustion treatment because you're not changing anything to the burner system itself, but on retrofits with massive FGR, porous matrix, and our technology, of course, you have to spend some money to get rid of the old system and install the new system. So there is a little bit higher cost involved here on the retrofits. Okay, we started this project quite some time ago. It was actually October of 2002. Really is when we had the initial meeting with California Dairies, the host site. And then, of course, there was a certain amount of time after that for design and production and whatnot. But this equipment has been in and running now for, well, a little over 11 months now. And other than having one failure, and I mean right up front, after about 1 day, we discovered that we needed to redesign a certain component in the system, but we got that changed rather quickly. But other than that, there's been no durability problems whatsoever on the equipment. Okay, we talked about this flame radiation and how some of these systems can reduce this radiation and the flame can get rather translucent. And we kind of touched on what effect that has on the heat transfer rate, the radiant heat transfer rate through the furnace wall and into the boiler. But also this translucent flame problem with using standard flame detection equipment. So this is another advantage that we felt we were going to be able to offer. We don't have any small orifices such as are there in these porous matrix burners, so we don't have to worry about combustion air. Again, no ceramic fiber or metallic material that's involved in these porous matrix burners, or, of course, catalyst materials in the post-combustion treatment. Now, safety issues. Flame stability, I think, is the biggest asset that we have to give here. We're not operating on the ragged edge of flammability, so if something changes a little bit, maybe some linkage slips, or the temperature changes drastically, or the humidity changes drastically, and at the same time you're trying to change firing rate, there's been many problems involved along these areas. Flame retention, we haven't had any flame retention problem. Flame retention is really anchoring, if you will, the base of the flame onto the face of the burner so that it's not floating around in places where you don't want it. Okay, as I mentioned, we've got 5 different flame zones, and we feel that this is really helps us in this stability issue, and also helps us on the turn down, the noise, and the lack of any instabilities on the flame front. And this acoustic coupling is something that can be a problem on some of these burners, particularly if you're trying to approach a perfect mix with the fuel and the air, as we looked at back along with the massive SGR burners. This acoustic coupling is, you could think of it as standing sound waves in a furnace, and under certain conditions, and if the geometry of the furnace is correct, these waves of a certain frequency will actually create combustion harmonics, which is very annoying to anyone who's around, but can also actually get a boiler to jumping around off the ground, and can be very destructive. But we have had no problems with this combustion harmonics. Now, in this control system, some of these burners that have been known to be unstable have these manufacturers have gone to what we call active control systems, whereby they're monitoring the O2 in the flue gas, which is fine. It's even more expense, and it's even an additional maintenance problem, because these O2 sensors typically foul quite easily. Some jobs we have seen even have had vibration sensors installed on the burner system. So if they do get too unstable, they'll shut the system down. Well, certainly not the best situation for industry. Okay, so we want to go into how is it that we're going to go about reducing or getting rid of some of these costs that industry has been bearing. I'm not sure this has been totally documented, but it's read in numerous places that the feeling is there's over 200 reactions involving more than 20 different species during the combustion process, and it is a rather complicated thing. But our thoughts and our goals were to utilize some of these intermediate reactions that take place in a certain portion of the flame and in a controlled manner, and utilize them to our advantage in the formation of NOx in the first place, rather than just trying to get rid of it after it was formed. Now, some of the things that we were looking for to take advantage of partially oxidized fuel. CHI standing for CH1 or CH2, CH3, partially oxidized hydrocarbons. CO and soot. And it may seem a little odd that a burner manufacturer would actually want to intentionally produce some of these items like CO and soot, but we're not going to get too much into chemistry, but we're going to attempt to show briefly how these things can be put to use to our advantage. Now, an amine species is something else that we were looking for, NH1, NH2, or NH3, which is ammonia. These things are all helpful in eliminating the production of NOx in the first place, under certain circumstances. And I want to emphasize that, under certain circumstances. Now, these components that we are looking for are formed in a reducing atmosphere. And when we get into looking at the equipment itself, we're going to see just exactly where this reducing atmosphere is and how we go about controlling these items that we're looking for. Just put a little note here that reducing atmosphere, what we're looking for is a stoichiometry of less than 0.6, which is, it's a fairly rich mixture, but certainly not uncontrollable and not close enough to the limits of flammability to cause any instability problems. Okay, brief look at two of the real basic equations of NOx formation. Of course, there's many other complicated ones, but just wanted to review that real briefly, but we want to spend more time on the reduction part. One thing we're looking at here, partially burned hydrocarbons. Now, I put a note on here, reversible, and this is true because the presence of this hydrogen cyanide actually can go back the other way and produce NOx under certain circumstances. And we're going to take a look at those circumstances. But here's another reversible situation involving hydrogen cyanide, and depending upon the environment, this reaction can be driven one way or the other. Carbon, this is our friend the soot that we mentioned before that most burner manufacturers don't want to make, but we do in certain controlled circumstances. Another reducing agent for NOx, and then the amines that we talked about, mainly ammonia, but the NH1, NH2 do come into play also. Now, I mentioned that under certain circumstances, these things are good, and those circumstances, once again, are in this reducing atmosphere that we are going to create in part of our burner system. Now, some of these other nasty players here, like the hydrogen cyanide and cyanide and whatnot, these things in what we call the final burnout zone are actually converted back to molecular nitrogen, CO2, and water, which are nice things to have compared to some of the other things we could end up with. I'd like to touch on prompt NOx real briefly here. Is a term given to those NOx molecules which are formed very early in the combustion process. And in fact, it's been where it's commonly believed that almost all prompt NOx is formed in less than a millisecond after the combustion process takes place. Low NOx burners up to this point typically haven't dealt too much with prompt NOx, and it's something you can't deal with after the fact. You have to deal with it up front. Another little fact about prompt NOx as opposed to thermal NOx is that prompt NOx is not affected by flame temperature very much, whereas thermal NOx is affected greatly by flame temperature. Now, we mentioned these reversible reactions before, partially oxidized hydrocarbons and these hydrogen cyanides and whatnot. These can actually, and these are some of the intermediate species that are formed in the very early stages of combustion and can, in the presence of oxygen, actually contribute to the formation of prompt NOx. However, what we're looking for is a reducing atmosphere. So in a reducing atmosphere, this is when we can reverse that reaction and actually use these things to our advantage to reduce NOx. Now, once again, we're in this rich portion of the burner in what we call a reactor, trying to keep the stoichiometry less than 0.6 and the temperatures below 2400 Fahrenheit. These seem to be ideal conditions for the formation of some of these intermediate species, the amines and the cyanamides and whatnot that we are actually looking for to prevent the formation of prompt NOx. Now, I'm not a chemist, and I don't intend to dwell on this too much here, but I did want to take a look at some of these chemical reactions that are going on here and that we're looking for. We start over here with NOx in the upper left-hand corner. NO and NO2, they're can be freely exchanged back and forth depending upon the environment. Sometimes one is more happy than the other. It's been our experience that NO2 is a very, very small percentage of NOx that is formed in combustion unless you got very high O2 or excess air conditions, and lower temperatures seems to be a factor in creating higher percentage of NO2. And if we look over here, we got our partially oxidized hydrocarbons here, which gives us hydrogen cyanides, and also in the presence of carbon, which is the soot that we were looking for, and in the presence of some water vapor, which we've got, of course, in the combustion process, leading us all back over to what we're really looking for, which is molecular nitrogen. And also we've got our amine species here, which reacts with the NOx to form the molecular nitrogen. Okay, so how are we going to go about all of this? We have here a cross-sectional sketch of what we envision this system to look like. We've got two different fuel streams here. We've got a rich fuel stream being fed into here. Oops. And this rich fuel, I'll get my arrow back here, comes out of these little jets and is mixed with air in these little mixers here. And that fuel-air mixture is partially combusted inside this refractory-lined reactor. And there's some things we found about this reactor that are quite critical, and that is retention time of the products of combustion within the reactor, and also the exit velocity of the gases which are discharging out of this port right here. And that would be the port that the rich fuel-air mixture would come out of. Now also the other fuel stream is the lean fuel stream, and it's introduced through these gas jets in 4 different spots around the perimeter of the rich reactor. And then when these products of combustion are discharged at a fairly high velocity out around the perimeter of the rich flame. And one thing I'd like to point out here quickly is the shape of this port here, where the rich fuel air is exiting out into the furnace. And the reason that is shaped like that rather than round is because we want this lean flame and this lean flame to mix with the rich flame at a different time and at a different place than this one and this one. So there's some critical dimensions here. The exit velocities on all 5 of these jets are rather critical. Just to kind of show briefly here in graphical form, we're bringing in our rich fuel with some air, and we're partially combusting it inside of this reactor. And then we're bringing in our air and our what we call our lean fuel, mixing it in 4 different places around the perimeter of that. Then we're bringing it all together into this final burnout zone downstream. And for this particular project and under certain circumstances, we may or may not want to bring in some FGR and also blend that into the final burnout zone. Now this rich reactor, it's producing this CO and soot, and there is some NOx, yes, there's some hydrogen, and some of these, what we call these nitrogenous reducing species, which would be the ammonia, or NH2, NH1, and so on. After all of these intermediate species leave the reactor, then we combine them with these products of combustion from the 4 lean mixers and blend everything together in a certain manner and in a certain time frame so that we can get the results that we want, which would result in, here again, this stable combustion, no CO problems, very low NOx emissions. Now, if we look at the reactor itself, I mentioned that that port, of course, its design, we went into that a little bit, but also the exit velocity of the combustion products out through that port is rather important also. And the exit velocity is quite high intentionally so that it will create recirculation zones in the furnace. And actually, if you can think of flue-gas recirculation system, it's essentially a flue-gas recirculation system within the furnace itself, as opposed to bringing it out from the stack and back through the burner. But we do look for this recirculation of hot products back into the combustion products. And we kind of touched on the controlling the production of this prompt NOx by creating some of these nasty players here that fortunately we're able to convert back to molecular nitrogen back out in the final burnout zone. And once again, some of the species that we're trying to create in the rich reactor. This flame is highly radiant, which is good for heat transfer, as we touched on before. It was actually one of the drawbacks of certain other types of low NOx burners, and also so we can utilize standard flame detection equipment, keep the cost down. So this one other thing that we were looking for that we were successful in obtaining. If we look at some points about these 4 lean zones around the perimeter, these are very lean premix flames. Here again, premix meaning, well, we're mixing the fuel and air here and we're kind of burning it there. It isn't, we call it near premix because there isn't too much distance between the point where we're mixing and burning, but nonetheless it is a premix flame. And lean premix flames have very low, they produce very, very little NOx. Thermal NOx production is low. Prompt NOx formation is also very low. So some qualities that we were looking for there. Now these particular flames, or the discharge on the mixers themselves, are designed for a very high velocity laminar flow, as laminar as we can get it. Could be some design problems with that as far as flame retention is concerned. We kind of talked about this rate of flame propagation and the rate at which you feed the fuel-air mixture. If it's too slow, you can have a safety problem. If it's too fast, the flame front's going to want to move off of the burner. But we took care of that by directing a very small percentage of these gases from within the rich reactor towards the discharge of the lean mixers, and provides a continuous source of ignition. So that flame front is anchored on there, and it's one of the other factors in our ability to obtain a very stable flame front. The excess air that's available from these 4 lean flame zones is actually what we use for the final CO burnout from the price of combustion coming out of the rich reactor. Now these lean flames also, they're very close to the walls of the furnace. We do that so we can get a rather high rate of a quenching effect, cooling from the furnace wall, if you will. And this has not been a problem. Conventional burners, this can be a problem if your price of combustion get too close to the furnace wall too early in the flame. You usually end up with a CO problem, but we have very little CO or unburned hydrocarbons in these very lean flames. Okay, here again we've got very high exit velocities coming out of these mixers. At it's around 140 feet per second, which here again creates these recirculation zones of these gases in the furnace, which we're using to temper the flame, bring its temperature down. If we look here real briefly, this chart was scanned in from another project, and so the text is a little fuzzy, but what we're looking at here, here's this lean, well, this is a premix flame right here, and also a premix flame with FGR. But we can see here, over on the right-hand side where it says fuel lean, which is where we're operating, over in this area right here, that this is, the NOx formation at this point is considerably less than at this point. And so now over here on this side, this is actually what we're looking for within the rich reactor. We're operating over here on the left on the fuel-rich side over here. Okay, so this is where we're operating within the rich reactor. In the center, here's where we're operating with the 4 lean combustion zones around the perimeter. Now the third important part, the final burnout zone. This is where we combine everything together, including the flue-gas recirculation, if we use it. Combines for the good CO burnout. All of these intermediate species that we talked about before, they're exiting the rich reactor, which we actually were looking for to reduce the formation of prompt NOx. Some of these intermediate species are still present when we reach the final burnout zone, which we use to reduce thermal NOx. Okay, the temperature of this burnout zone is relatively low, mainly due to the excess air from the 4 lean flame zones, and also the mentioned previously that we like to control the temperature within the reactor to less than 2,400 degrees. Typically around 2,300 seems to be a pretty ideal temperature. So our flame temperatures are not that high to begin with, but we can go down further with the introduction of FGR in the final burnout zone. Now, I mentioned if we use FGR or if we don't. the critical factor here is how low do you need to go with your NOx. Test results have indicated that without any flue gas recirculation at all, this system will develop no more than 17 or 18 parts per million of NOx with absolutely no FGR. If you need to get down to single digits, we can add FGR. If you need to get down around the 5 or the 6 ppm level, it requires about 25% recirculation. Here again, this nasty soot that most people don't want to make, but we do. As this goes through its final burnout stage in the burnout, we get most of our favorable radiation for the heat transfer and also for the flame scanning. So the result of all of this, as I mentioned, we get 17 or 18 parts per million without any FGR. 15 to 25% FGR, depending upon what sort of requirements you need to meet in your locality. The system is, this particular project was mainly geared towards fire tube boilers. There has been some laboratory testing done applying this technology and burner design to water tube boilers, and it looks very encouraging. Now, take a look at the equipment itself and what all this stuff looks like. You can see over on the left here, the burner system. We can see the reactor here. This is the downstream portion of the reactor, if you will. This portion of it actually fits inside the furnace. And this is, you can see a couple of the lean mixers here, one here, one up on top over here. We've got our gas control valves here with some servo motors on it. These servo motors, and in fact the whole combustion control system is controlled by a microprocessor-based system. Closed loop, got total feedback on everything, so we know we can monitor the position of all of these valves. Actually, not just the two fuel valves, but we also have the one channel for combustion air and one channel for flue gas recirculation. This is a look at the business end of what we got here, and you can see this funny shaped exit port on the reactor here, which is we went through the purpose of that. This is a view of the equipment from the back end of the reactor, and this is with the blower housing swung open. This burner design has a swing away axial flow fan so that the customer can have access to all these components inside here. You can barely see some of the rich mixers here, which deliver the fuel air mixture into the rich reactor. And we can see our lean fuel jets here, which are at 12, 3, 6, and 9 o'clock. Then a few other little items, flame scanner, pilot, et cetera, et cetera. All of these components are removable if need be. Okay, this was the existing system that was at this host site prior to our starting this project. As you can see, this was an induced FGR system. This is the FGR being brought back from the stack of the boiler and just fed into the inlet of the combustion air fan. This, when it was installed, the NOx limitations in the San Joaquin Valley at that time were 30 ppm for this size boiler. That is no longer the case. 9 ppm is the max. But on the last source test taken on this equipment before we took it out, these were our benchmark numbers that we were looking at here in the middle of this chart, the existing numbers. These were taken by a third-party source test. You see the NOx here at 25.3. CO, fairly high, 70.2. Stack O2 fairly high at 6.2. Now here's what we were shooting for on the numbers. 5 to 6 parts per million on the NOx, less than 50 on the CO, and we also wanted to get this O2 down into the 3% range. So, bottom line is we wanted to try and reduce the NOx by 75% and the O2 by roughly 50%. Here again, what's the advantage of reducing the O2? Goes back to how much gas this customer can save simply by getting rid of this excess air that's not required for combustion. Here's a picture of our equipment when it was installed. This one did utilize flue-gas recirculation, which is coming down this pipe here, and we used forced recirculation on this job with this fan. Oops, sorry. There has been some laboratory tests done with induced FGR as opposed to FGR, or forced FGR. I mentioned earlier that to get down to the 5-6 ppm levels, 25% of FGR is required, and I should state that that is on forced FGR systems. Induced FGR systems, only 15% FGR is required to get down to these 5 to 6 ppm levels. Here's an actual photograph that was taken from the downstream end of the furnace, and you can see the high degree of radiance that we're getting from this flame out of the rich reactor. It's really kind of an eerie sight. Looks like something you'd see on the Sci-Fi Channel even. But around the perimeter, you might be able to pick up this little bit of lighter blue color here, which is those real lean premix flames. And we're introducing the FGR in 4 locations around here and here and here and here. And then, of course, downstream from all of that is the final burnout zone. On this microprocessor-based control system, we actually had 14 points throughout the firing range where we where we programmed this fuel-air curve. We couldn't fit them all on here. You wouldn't be able to read them, so we just took 2 intermediate ones and the minimum ones just to kind of show you where we ended up in relation to where at the beginning of this project. O2s, I mentioned before, we were able to run actually less than 3% without any negative effect. Mainly, usually what will happen there is on a lot of burner systems is the CO levels will become intolerable. But at the higher firing rates, we had absolutely 0 CO. You may recall our goal, I believe, was less than 50, if I'm not mistaken. We were a little bit higher than that at minimum, and I think that was just due to one little quirk on this particular installation that we decided wasn't worth tearing all the equipment out and redoing it, but there was a little bit of excess flame impingement at low fire on the furnace, which we are 100% positive is causing this 75 ppm CO at low fire. NOx levels, we were able to get down there at, we even saw some numbers less than 5 at certain points, but these are actually numbers that were taken. These are average numbers that were taken over a 10-month period. It wasn't just one snapshot in time. The effect of FGR, mentioned before, over here on the left-hand side of the chart, we were looking at about 17 parts per million with no flue-gas recirculation at all. And we gradually blended more and more in until we got down to this area here where at some firing rates we were actually even a little bit lower than this 5% as indicated by this graph here. So a little bit of summary of the technology. Our goal here really was to create some of these weird species, if you will, to try and eliminate the formation of NOx in the first place, as opposed to making it and then trying to get rid of it downstream. We feel we've been pretty successful in doing both, eliminating the formation up front and reducing what has been formed downstream. We feel the combustion characteristics we got were, compared to other systems that are on the market now, were just extremely favorable, particularly the fact that we were able to modulate this system between the minimum firing rate and the maximum firing rate as fast as we wanted. The system didn't care. It had no signs of instability whatsoever. Very low CO and unburned hydrocarbons emissions, also very favorable. The construction itself, probably couldn't tell just from looking at the photographs, but looking basically at some rolled steel, a little bit of stainless steel, and some refractory material used in the combustion industry forever. So the cost for us to manufacture this equipment and supply it to industry is considerably less, and that's going to depend on the exact capacity of the equipment. But there's going to be some considerable savings for California industry on the initial cost of this equipment. Plus, we've also gotten rid of this need for ongoing cost as far as replacement matrix materials or replacement catalysts or the ongoing cost of chemical injection, et cetera, et cetera. And main goal is single-digit NOx, because without single-digit NOx, we are kind of spinning our wheels. Well, so it all sounded fine and dandy, and we spent considerable amount of time monitoring this thing. Any problems? Yeah, you betcha we had problems. We had one very big problem, which was recently, and it was a very embarrassing problem, actually. After 10 months of testing and testing and testing and following this thing and everything's fine, we didn't pass the source test. We failed the first source test. Couldn't believe it. Well, as it turns out, there was actually a couple of reasons. We had...
What were the numbers? Was it 9 dBA for the source test?
Yes. Yes. And we were running at 5 and 6 prior to that. Yes. We did not pass. We were running 14. We said, my gosh, what happened? Well, we had just purchased, one thing that happened was we had just purchased a new analyzer, a portable analyzer, which had been calibrated and whatnot, and we relied on it, but what we didn't know is we had a faulty sensor. So we went down a few days before the source test, and we said, oh, we need to make a few changes here and there, which we did, and it turns out they were not the correct changes to make. But we didn't know it until the source test had already started. The other problem that we had was that these little servo motors that are run by this microprocessor-based combustion control system have these little feedback potentiometers on the drive shaft, which sends a signal back to the microprocessor and says, hey, you told us to be at this certain position, and I'm sending you the signal back here telling you I'm there. Well, it wasn't. So we had a faulty feedback on one of the drives, and as a result, our O2 levels were changing. We had a lot of hysteresis in the air supply. Well, fortunately, we've pinpointed all these problems, and we did manage to get the source test people back in there and the district engineer back in there a few days later, and so fortunately we got over that. But that was quite embarrassing after all this time and money, and so at any rate, we feel like we've met the goals of this project. Now, this $900,000 figure that's here, that wasn't just for this portion of the project. This is money that's been spent over the past 4 or 5 years, actually, in developing this technology from concept to now proving it in the field. As far as laboratory tests are concerned, numerous sizes, 2,500, 300 horsepower. This particular field test that this project was about was 500 horsepower. And we feel like we've really met all of the goals, and we feel like we're going to have a product here available for California industry. It's going to make it a whole lot easier for them to meet some of these new regulations, particularly, for example, in the San Joaquin Valley. We just changed their regulations in September, and it's going to be an awful lot of industry that's going to have to replace equipment that's not that old. So it's going to be a little bit more palatable for them. The aftermath of all of this, our company, ST Johnson, and Altex Technologies, the holder of the IP rights, we've signed a 20-year licensing agreement not too long ago to utilize this technology in the production of commercial burner equipment. And also, I mentioned I'd put both sub 15 and sub 9. Actually, our intentions there are we can easily induce a little bit of FGR, just a couple of percent, for these systems that are only required to be sub 15. Those would be, for example, in the San Joaquin Valley, would be those systems that would be less than 500 horsepower. 500 horsepower and above has to be sub 9, of course. There we would utilize this forced FGR. Last January, we were an exhibitor at the International Air Conditioning, Heating, Refrigeration Exposition down in Anaheim. We up one of these systems and took it down there for a little show and tell, and we actually received honorable mention for most innovative product at the show, and that was like, I think there was 1,800 exhibitors there with products. So we were pretty happy about that. There's been several systems purchased already. The first one has been installed, and in fact, next week, hopefully. We're going down there to commission. We just hope we don't run into some of the problems you sometimes can. But so the wheels are already rolling as far as making this technology available to industry. Okay, we're also in discussions right now into taking this technology and not just going up in size in burner equipment, but also coming down in size. Perhaps even driving back for small combustion systems, which most places right now are 30 ppm or less, or 25 ppm or less. We feel that we can manufacture some equipment utilizing this technology, which will be economically feasible and still bring down these NOx emissions. So, in conclusion, I thank you all for attending, and don't know if you have any questions, but certainly we need to thank the California Air Resources Board for the ICAT grant program, which I feel certain that at this point in time anyway, this technology would not be available to industry if it were not for this program. So we have to thank California Air Resources Board. Any questions? Can you say?
How sensitive is technology to changes in BTU content of the gas?
Good question. One that actually has been asked by a potential customer. There's been some preliminary tests done on propane. And I don't think I specifically mentioned all of the tests on natural gas. But there has been some tests done with propane. The NOx numbers are a little bit higher, but we can still get single-digit NOx by utilizing flue-gas recirculation. From the valley, sun-made raisins has a lot of digester gas available. And we feel we could probably get single-digit NOx with that particular type of fuel without any FGR. We've done some testing with conventional burner systems with these lower BTU fuels, and particularly this digester gas and whatnot. There's a lot of inerts in it, burns slowly, and it's not good at generating NOx. So I think by utilizing this technology, we feel we can get single-digit NOx without any FGR with those types of fuels. But then going the other way, the propane or what we've done no tests with anything other than natural gas or propane at this point in time. How far you were thinking, maybe butane or whatever, I don't know.
Well, variabilities just in terms of natural gas, in terms of methane, but with increased butane, propane contents.
Now, are you saying that on a given installation, maybe the heating content would change?
Yes.
Good question. Very good question. I would have to say that if the emissions requirements were sub-9, and of course it would depend on how much this variance was in the heating value. But one of the real tricks of this technology is to operate pretty close to a certain stoichiometry. And my feeling is if there was very much variance in the heating value of the fuel, that we may want to or may have to include a O2 trim system on the system. And the response of that might not even be fast enough to keep the NOx levels below or down into the single-digit numbers. That's my gut feeling, although we haven't really played around with that yet.
So now it doesn't include an O2 trim. It's set up for.
You could, but it's not required.
Okay.
It's not required. Yeah. We feel very confident that these new microprocessor-based combustion control systems, which are on the market today, they're becoming very commonplace, and the cost has really come down on them. This particular project utilized a 4-channel combustion controller for the rich fuel, lean fuel, the air, and the FGR. And gosh, with the controller and the servo motors and whatnot, it wasn't really much more expensive than a standard conventional linkage type system, utilizing maybe adjustable characteristic control valves, et cetera. Hardly any additional cost at all. So, but we feel that type of controller is more than sufficient to be on this type of system.
Thank you.
So would you claim, as compared to the other 9 ppm burners, that the high capital costs and high maintenance costs can be offset by higher efficiencies, operating efficiencies, which means using lesser fuel as compared to the old traditional or higher conventional burners and getting higher heat transfers? Would that be true in this case?
Well,
Well, that's their claim.
well, I mean, if you look at some of the data that we've taken and some of the data that some of these manufacturers readily admit to, for example, these porous matrix burners, they readily admit that they operate with 65% excess air. They have to. Well, how can anybody claim? I mean, you've got 9% O2 in your stack, or 7%. I don't recall what it was. I think 9. everybody in the world knows that you're going to have to burn more fuel to get the same output out of the boiler. I didn't quite understand what they were claiming about. You said something about increased efficiency. Are you saying they're claiming more?
As compared to traditional conventional burners, you've got high capital costs with the new 9 ppm burners. I'm talking about Todd Radiant and Cohen and there's another Canadian manufacturer, I forget.
Matcom?
Matcom, right. So what they claim is higher capital costs, higher operating costs, but that can all be offset by higher efficiencies in the burning process, in the combustion process.
Okay. And probably
I'm not talking about matrix burners.
Yeah, I know the type of burners you're talking about, yes. But they're probably comparing them to the matrix type burners.
Okay.
And that's where they're getting with the increased efficiency.
Okay.
That's where they're coming from there. Yeah. Yes, I would agree. They can probably justify saying that. What the payback period is, I don't know, because these systems are quite expensive.
Right, I think about 5 to 10 years. Yeah.
Yeah. But one of the goals here in looking at the costs for us to manufacture, I think we can offer the higher efficiency without the higher cost.
Right.
So why pay more if you don't have to?
Fair enough. I have another clarification. You called your primary as your lean burners, and the secondary burners was the rich burner, right in the middle. That's what your chart showed. Is that correct? Most other manufacturers call it the other way around. That's okay.
I would call it the other way around, too.
Okay, that's what I thought.
You're talking about that chart that...
Yeah.
Oh.
And you also called...
You know what? I didn't make that chart up. Somebody else did, and
That's what I thought.
Maybe I should have looked at it more closely. But no, I would consider the rich reactor the primary.
Right.
Yeah.
And my last question, I don't see the difference, or at least I don't understand the difference between induced and forced FGR in terms of going from 15 ppm down to 9 ppm. What difference does it make how we pull the FGR into the combustion zone, be it forced or induced? I don't understand that concept.
Well, mainly it has to do with how effectively you can blend everything together. With forced FGR, typically you're not utilizing the flue gas as efficiently as you are with induced, because with induced, when you bring it in along with the combustion air, I mean, everything is intimately mixed up.
Pre-mixed, right.
Yeah. Whereas with forced, you actually have to try and get this stuff to go where you need it, and it can be rather difficult to do. And that's why it's been our experience that with forced FGR systems, it always requires more recirculation than with induced FGR systems to get the same results.
So you get better combustion parameters with induced FGR as compared to a forced FGR system.
Well, I think you can get the same parameters, but
Lower
but-
emissions.
The emissions are going to be about the same.
See, that's what
But I think you can do it with less energy and by recirculating less FGR. And there's also one less fan involved, which a lot of customers don't like forced FGR systems. Quite frankly, it's
And most of them are the
One-
induced type.
yeah, it's one more piece of equipment you got to maintain. and
Right.
Makes no. Yeah.
Fair enough. That's all. Thank you.
Do you think that you're going to shoot more at the retrofit market or at the new burner market?
Well, historically our firm has marketed more towards the retrofit industry, but of course it doesn't have to stay that way. We know that there's going to be an awful lot of retrofit business going on out in the valley, for example, in the next 2 years. I think the district said there was 1,600 boilers and fired heaters that were going to be a result of this new rule last September. I think we estimated that out of those is probably about 1,200 boilers. That's a lot of retrofit. And for us, that's, if we could get, we're not a very large company. But news travels fast in our industry, and there's no secrets. And when we went to this International Air Conditioning, Heating, Refrigeration Expo that I mentioned in January, we were approached by numerous boiler manufacturers who just, like, when they opened the doors, they were screaming over to our booth. That's never happened before in our company's history. So we feel that we probably will be involved more in the retrofit industry, side of the industry, but there's been a lot of interest from boiler manufacturers. And it appears that the biggest driving factor there are their distributors in California who have had this other equipment jammed down their throat, and they don't like it because it's been a lot of problems for them. So they're looking for something different, and there's been a lot of interest. So where it ends up, I don't know, but I'm sure that we won't turn down either market.
Okay, thanks.
There was a question from an online viewer. Will the slide show where?
Yeah, we'll post it on the web once we get a PDF file from S.T. Johnson. So it'll be a couple of days, I guess, but it will be there.
Yeah.
Any further questions? Well, thanks very much, Dan, for a very informative talk, and thanks everyone for attending.